The theory of model-based approaches in phylogenetics are described quite well by a variety of people and are pretty well understood by many students. But once you get into the nitty-gritty of implementing phylogenetic methods, there's a lot of really key decisions that are a lot less clear. And so I was really hoping to talk to several people who have implemented phylogenetic tools, and I hope to start with you, of course, given how important your contributions were to developing the theory itself, and then the very first workable tools, software tools for using models in phylogenetic inference. And we've talked about parts of this before, and I've thought back to some of those conversations, and I have a few open questions from that I was hoping to get to as well. And I guess maybe to back up a little bit, first of all, I was hoping to talk for a few minutes about your introduction of likelihood approaches to phylogenetic methods. And I was wondering,
by the way, which I didn't do.
Okay. So why don't you set the record straight?
Yeah, the very first person I know of who used likelihood on phylogenies was Anthony Edwards, in work with Luca Cavalli-Sforza. 1964 is the first publication they have describing that or mentioning that. I come in after that.
Yeah.
And the first molecular sequence, use of likelihoods in molecular sequences, is by the very famous statistician Jerzy Neyman in 1971 in a statistical decision theory volume. Which I think Alan Wilson had something to do with getting him into that. So,
okay.
Yeah.
So it's something that was in the air then. I mean, were you thinking about their work when you decided to dive into this, or were you motivated by other things and then came to it and discovered their work and then expanded on it?
Well, I got into it in graduate school when I was working with Dick Lewontin, and I was doing some population genetics model that never succeeded. And but at the same time, Jack Hubby, who Dick Lewontin was working with in his electrophoresis work, and a very progressive-minded taxonomist named Lynn Throckmorton, whose work on Drosophila is very well known. They came to me with some protein data that Jack had generated on with flies. He and Throckmorton had generated protein band data and wanted to make clusters of Drosophila. And I got writing. I was this graduate student who was messing with computers, so they came to me, and I wrote a clustering program, and then after that, I saw Robert Sokol's paper in 1965 with Joseph Kamen and Sokol, 1965, where they were talking about implementing parsimony methods in order to prove that they didn't work. They weren't trying to prove that they did work. They wanted to show that phylogenies wouldn't be obtainable. And Bob Sokol came through University of Chicago. He had been a graduate student there a decade or more before. Gave a seminar on that, and then I said, "Oh, that's interesting," and I tried to write a program to do that.
Wow!
And in the summer of 1966, I went to the International Congress of Human Genetics, which wasn't much of a trip because it was held at our university. So no travel, no accommodations, just a registration fee. And Anthony Edwards was there, and he introduced me to Luca Cavalli-Sforza, who was also there, and talked to me about what they were doing. And that's how I got into it.
Wow. Okay. Wow.
I get given credit way out of proportion. There's There are people out there who think I invented the notion of likelihood.
Right.
And I have to say, oh my God, is there a statistician around? I'm so embarrassed because
That's so funny.
Fisher 1912 or 1911, whatever it was, and even a couple people before that. So.
Wow. So that's really interesting that it was your existing expertise with computers, it sounds like, that was a segue into this for you. And where did you get that expertise? Because, of course, your brother also was into computers. Is that something that goes back to your childhood, or?
Well, it does, in the sense that I used to read. I used to go a lot to the Philadelphia Public Library, and I would go to the section on science. I would, and one of the things I started reading about were computers. I had no access to one. This is in the late 1950s when I was in high school. And the computers were like 10 years old at that point.
Right.
Most American universities had just gotten their first computer. I didn't have access to those. And I helped get my brother involved in, he was doing electronics, and I helped get him involved in an abortive attempt in our high school to have a computer club and build some sort of a binary circuit.
Wow, that's great.
And for technical reasons, that never worked, and he didn't get back into computers until later. But it wasn't directly from him, but it was from these books in the library. I guess I was interested in mathematics, and I was interested in biology, and I was fascinated by these computer thingies. And then when I got to the University of Wisconsin in 1960, in the spring of '61, I took a computer course taught by a staff member from their computer center, because there was no computer science. There were no computer science people available to teach.
Yeah, it wasn't even a field really at that point. Yeah,
it was just, here's how to program, here's how to submit jobs to the computer. And it was taught by the staff member guy from the, whose name I forget, from the, and so I started writing programs, and I started writing genetic simulation programs and genetic iteration programs, and those I was using in my population genetics. So
amazing. And so would that have been in assembly, or did you have COBOL or something at that point?
COBOL was around, but I never used COBOL. The University of Wisconsin had a CDC 1604 computer. And when I started those lectures, they had just gotten the machine recently. They had no assembler, but they did have a Fortran compiler. We were taught not assembler, but the octal numerical codes, machine code.
Wow.
He gave us one lecture on that, which was pretty hopeless. 014 is clear and add, and so on. And I was thinking, how could this is going to be hard to use. And then the next lecture he came in, he said, they just got the assembler working.
Oh my gosh.
So now you can say CLA instead of 014.
That is amazing. Wow.
But I did write mostly in Fortran 2, which was their Fortran compiler. And all my early work, except for some in BASIC, all my early work is Fortran.
Wow.
So,
okay.
Well, the early university computers, most American universities bought computers about the same time, 1957. And they bought like IBM mainframes, which were like a room full of equipment. You were given an account and you punched your program into cards. You used a card punch.
Yep.
And you took your deck of cards to you did that at the computer center. You took the deck of cards and you took it to a filing cabinet, or a filing cabinet that had drawers to hold decks of cards. And you opened it up and you put your deck with the the front of the deck had a card with your user number punched in it.
Wow.
You put it in there, and then once a day they would take that bunch of decks and run them through the computer and have the Fortran compiler compile each program and then run it. And that was it.
That's
The
amazing.
next morning you came back at 11 o'clock and they put the printed output in a rack, under your initials, and your card was, the cards they had used were in another drawer, and you look through and say, "Oh my God, it's a bug."
Yeah, right.
And you run and get your card, and then you competed with people for the punch card machines. You had 1 hour to find that bug and correct the statement and put it back in the drawer. Otherwise, you missed that day's compile.
And how did you have the methodological expertise to really innovate with the methods in the context of this problem?
Well, I was a summer student at the end of high school, between my junior and senior years, in the Jackson Laboratory in Bar Harbor, Maine. And the third summer I was there, which was now between my first and second year in college, I was in their college student program, and a guy in that program loaned me a mathematical statistics text, one of the early widely distributed ones by a guy named David Hoel, Hoel. It was pretty good. And I was reading through it, and it came across the chapter on likelihood. And I thought, whoa, this is, not only is this interesting, it's, it was clear that it was generally applicable method,
right?
Not just something cobbled together, but you could make up a maximum likelihood method by following that recipe. Although most statistics courses didn't teach about that, because to do maximum likelihood, you're usually multiplying together probabilities of things for independent pieces of data. And to multiply a lot of things, in those days we were working not with computers, but with desk calculators, mechanical desk calculators. And you really couldn't do it. You'd get underflows. So what you want to do is you want to take logarithms and add the logs and work with log likelihood. But a mechanical desk calculator can't do a log.
Really?
Yeah. So you had to use the only way to take logarithms is use a
table.
A table, which is too slow. That's too slow. So likelihood didn't actually become usable until you had computers, or you had a little bit if you had electronic desktop scientific calculators, which is a little later on. I mean, that's getting 1970-ish. So, but anyway, I learned about likelihood in summer of 1961, and so that influenced me.
Yeah. Wow. That's fascinating. So so these ideas were percolating. You had this computational background, this interest in statistics, and then eventually, so you talked about this early on in 73, and then your primary implementation was in 81. Was this something, did you set it aside in the meantime, or what triggered you to revisit it in 81?
Well, I'd actually been working on it. I got into fiddling with trees, programs to make trees. Anthony Edwards, I had something in my PhD thesis. My PhD thesis was supposed to be on population genetics, but my project had failed. And Dick Lewontin said, why don't you write up that tree stuff?
Wow.
So I did. And towards the end of the PhD, I have a section on Brownian motion, doing likelihood on trees with Brownian motion models. And that was the first time I figured out a dynamic programming method for likelihood.
So you worked it out for continuous traits before you did for discrete nucleotides.
Yeah, and
Wow.
and that was actually the case I innovated, but in the meantime, I was also keeping track, or sort of watching with interest without doing much in the field of statistical genetics, where people were computing likelihoods on pedigrees.
Mm-hmm.
And in 1970, 71, 72, three different groups came across dynamic programming for moving likelihoods up pedigrees.
So the pruning.
The pedigree is like, it's tree-like, it's upside down, and
Right.
so you move information up it. And there's a whole story, but basically somebody for one of those three groups sent me a preprint. This is a paper of Elston and Stewart in 1971, which is about these algorithms for computing likelihoods, so-called peeling algorithms, that later became called peeling algorithms. And I looked at it and I sort of said, oh, well, that's exactly what I've been doing with Brownian motion. And this is doing it for discrete traits. So I started thinking more about that. And in 1973, in a paper in Systematic Zoology, I have a section where it describes that algorithm.
Mm-hmm.
So, and I was, by that time, every year going to the numerical taxonomy meetings that Bob Sokol had. And I had run into various other people working on mostly parsimony methods, some distance methods.
Mm-hmm.
So as DNA sequencing became available in around 1977 or so, 77 to 79, I began realizing that people were going to be doing phylogenies with DNA sequences.
Mm-hmm.
They were already doing it with protein sequences.
Right.
So I said, I really should write a paper saying how you do that, even though it's implicit in this 1973 paper, but none of the molecular evolution people were going to see that. So,
right.
Or if they saw that paper, they'd never read that section. So I decided to, just in order to publicize it, to write the 81 paper. And I'd also started writing phylip and distributing it.
Okay. So,
yeah,
because you mentioned software in the 81 paper, and so it was a Pascal tool that people could write to you to request. I forget exactly what the available distribution mechanism.
By then it was in phylip.
Okay. All right. So that early tool was phylip, and then I guess later you ported it to C.
It was the dnaml program in phylip.
Gotcha.
Different functions in phylip, different methods were done in separate programs. It was dnaml, there's the whole story there of writing my own programs in Fortran and then switching to Pascal in the late 1970s, and then deciding that since Pascal worked so well on this, that I would try to put out a package.
Yeah, so I was just looking at, so you had said this package will be supplied on request, written in standard ANSI format on the magnetic tape supplied by the recipient. So I guess people not only had to provide a self-addressed stamped envelope, but also a tape to put the program on.
Yeah, at that point, yes, that was our, I guess I know people like me, old farts who use computers in the early days, we have endless stories, and I don't want to take up all your time with it. But if you distributed in the 1970s a program, and some people did. Walter Fitch had some programs and was willing to send them to people. But the way you sent them, you punched them onto punch cards. You took this deck of punch cards and you put it in a punch card box that would hold the punch card, cardboard box. And then you found out that because it had information on it, the post office wanted to charge you first class rates. And then you go down to the post office and they say, does it have any information on it? And you say, no, it's just blank punch cards.
Nice.
And then you could mail it at the parcel post rate, which is much cheaper.
Gotcha. That's
so
amazing.
you're mailing boxes of punch cards, and it was also possible to write, take a magnetic tape. It's about this big, and write it on it. But of course, if I said in the paper, send me a letter and I'll send you a magnetic tape, everybody and his brother would expect me to buy a tape and send it to them.
Yeah.
So the only way out of that to weed away the non-serious people was to say, you send me the tape.
Yeah. Oh, that's great.
Later on, people wanted to log into when we had interactive computers, time sharing systems later, people wanted to log in and then copy out the files. And I wasn't willing to do that because I'd have to be on the phone to the, so no, hit carriage return, and it would take half an hour of arguing with them before they got any files. So, really, magnetic tape was a possible way to distribute then, and I did some distribution of magnetic tape, but soon after that, microcomputer diskette formats were getting standardized. The IBM PC comes along in 1981, I think, and you then can say, oh, okay, send me some diskettes, and I'll write them on the diskettes and send them back, and that's much more practical. Yeah, in the 70s, Walter Fitch was willing to send you programs, and sometimes you could talk Bob Sokol or somebody into giving you a punch card, sending a punch card deck. And so there was this sort of informal distribution of just a few copies by various people's programs. Right. And the one that was sort of a breakthrough was not phylip. It was J.S. Farris's program Wagner 78, which was a parsimony program that he, I think, first put out about 1978, but by a couple of years later, lots of people wanted to try parsimony, and he was pushing it, but he wasn't really distributing it. However, it got widely stolen. He'd give it to a friend, and then a friend had a friend, and he'd say, well, don't tell Farris, but I'll give you a copy, and it was stolen widely. So the first distribution is stealing Wagner 78.
Wow.
Then I decided in 1980 in 79 and 80, I had a summer student, Jerry Sherman, working on writing Pascal programs for phylip, and we finally got it together in 1980 and distributed it around the end of October 1980.
One thing that's really interesting to me that is critical to implementing these tools and critical to a lot of methods too, but I don't think has received the attention that's due to it, is the actual computational representation of the trees, because different approaches lead you to think very differently about which trees are adjacent or more similar to other trees, what moves you're going to make as you search tree space.
Yeah, let me give you a little bit of an overview also of the tree representations that we used to use before phylip in.
That would be great. Yeah.
Fortran programs, because I was writing parsimony programs back in 1966, roughly. And so 14 years before phylip, I started writing parsimony programs. And let me see. Now, I think what I'm going to do is sketch something on a piece of paper and hold it up. Is that going to work?
I love that. Yeah, that's a great approach.
Okay, we'll try to do. So we're writing in Fortran. Fortran does not have pointers and objects of any kind. It's for a numerical processing using things like arrays.
Yeah, so it's much more like R is today.
Yeah, and we'll come back to that. Let me just scribble something here.
Great, perfect.
So I'll make a tree. Okay, so here's a small tree, rooted bifurcating tree. So we have a tree which is on your left. It's got 5 tips, and they're numbered 1 through 5. And then there are interior nodes numbered 6, 7, 8, and 9.
Yep.
And what we used to do, what I did in 1966 was have 3 arrays. The nodes are all numbered. There's an array of left descendant. That's the first column. Yep. The first column is just the number of the node. And the second column is left descendant. And the next one is right descendant. And the third one is ancestor. So you'll see if you go through this that those encode the structure of that tree. I put zeros wherever there isn't, wherever there's no descendant. Yeah. No descendant or no ancestor. And the other thing that's interesting about this one, it's very quick. You can encode it as it's hard for me to point to it, but each one of those is a one-dimensional array.
Yeah.
And when you're working in the Fortran era, a two-dimensional array is slow to use because you have to compute the index, you have to do a multiplication and an addition. But if you have a one-dimensional array, it's quicker. So we would have 3 of these arrays: left descendant, right descendant, and ancestor. And if you wanted to move information down the tree, you could do it over here by if you ordered the nodes so that descendants always have a smaller number than ancestors.
Right.
Or than their ancestor.
Yep.
Then if you go over to these arrays and you just go down, you can just use that and process the information. And instead of recursive pointers and records and tree traversal, you're just doing bookkeeping coming down these arrays, and it works. But there's a catch, and the catch is that when you rearrange the tree, when you pull somebody out and stick them in somewhere else, if you want to maintain that order, you have to go do a certain amount of bookkeeping. So I had to do that. So this was the Fortran tree representation I used, and it's fairly straightforward and obvious. And recently I ran into, when I was talking to Dave Swafford, I said, Dave, is that the way you used to bookkeep a tree when you wrote Palpstar? And he said, yeah, I did it that way. And I think that's not surprising that people would come to that. Well, the interesting thing is, in the R era, the people doing R discovered a magical new representation of the tree. That you could do it with arrays. Right. Back in the 60s and 70s, and then in the 80s when distribution of programs really got off the ground, everybody was inventing all these bookkeeping methods.
Mhm.
And nobody was publishing them for the very simple reason that the journals would not have printed them. If you went to a biology journal, they would say, I don't need you to tell me the bookkeeping that you use inside your program. I'm not going to waste precious scientific publishing space, so
Right.
you can brag about your bookkeeping in your program. That's not important. And we knew we couldn't publish it. And we just thought, this is the method I happen to use. Other people will use other methods. Who cares? Later, it became possible finally to publish the algorithms. And so you see people publishing things like tree rearrangement strategies.
Yeah.
Almost all of those had been used earlier by other people.
Yeah.
And invented multiple times.
Right. Absolutely. In part because they're not being published. So that really helps explain this big gaping hole in the literature of the field. And I think there's a tendency to think that, this is just this black box thing, like as long as it's encoded in your software and working, it doesn't matter. But I think it really does, because then we have concepts like Robinson fold distances and things that are dependent on how you're reorganizing these representational structures and parts. So it does emerge back out and bubble up and really impact the way that we think about the biology.
And we also could not have published it in math journals, because the mathematicians would say, you're not a real mathematician, and this isn't really mathematics, it's just bookkeeping.
Mm-hmm. Mm-hmm.
We're not going to publish something stupid like that. So, you couldn't do it. You were referring to the methods for inferring the tree and then the methods for using the tree. And that is kind of a sore point, because back then, if you had molecular sequences and you had either statistical or non-statistical methods for inferring the tree, let's say statistical,
Mm-hmm.
and then you had some quantitative, some morphological characters, let's say, that were quantitative. I understood pretty early on that in principle, you would want to infer the tree and infer things like covariation between characters.
Yes.
All at the same time, because I had been working on these Brownian motion models, and I started working on them when they were modeling gene frequency changes, and those are independent, roughly. And then I started thinking about quantitative characters, because I was a population geneticist. I had studied quantitative genetics. My postdoc was in the quantitative genetics group at the University of Edinburgh. So I was very aware of that. And I started thinking, well, how could you do it if they're quantitative characters? And then I figured out you'd need to know the covariance matrix of changes. And so I sort of knew how you would have a quantitative genetics model and how you would have a molecular model. And then you could say, well, if you want to infer the covariances, let's say, you would want to keep you'd want to use the molecular and the morphological data to infer the tree.
Mm-hmm.
And as you change the covariances, you'd have to redo it. You would have to, the whole thing would interact. And so I actually mentioned things like this in my 1985 comparative methods paper. But nobody basically could, there are two problems. One is it's computationally very hard. It would be a lot of computational work. And secondly, the DNA data coming in was getting so huge that after a while, pretty much everybody said, use the DNA to get the tree. And then interpret the quantitative characters. And yes, in principle, having done that, you have a little extra information about the tree, but it's kind of trivial in amount. So everybody kind of gave up and said, you know, we won't do this whole thing as a unified inference, but we'll just do it as a two-stage inference with
yeah, it's changing so fast now, because of course now there's these very high throughput phenotyping approaches. For example, you know, collecting lots of morphological landmarks at scales, you know, on par with often what we think of for molecular data. But then the other thing that's really interesting, I think, right now is using phylogenies for looking at comparative genomic data, so looking at evolution of expression and things, and these are quantitative traits. So it's really interesting to hear you say that to a certain extent, some of the continuous trait methods, the development, just those were put on ice a little bit while the discrete methods went ahead. And now we really need those continuous methods. And for example, one of the biggest obstacles that we've come up against is that most of the continuous trait methods seem to not accommodate missing data. Is that for a statistical reason, or is it just more engineering that hasn't been done yet? Like REML methods, both in phylip and RedBase, I believe, for example, you have to have a complete matrix.
Yeah, and I can sympathize. I faced that long ago. And in principle, you can do it. In principle, there is no, the statistics is straightforward. There's no people will say things like, well, what you'll have to do is reconstruct the missing data.
Exactly, yeah.
And I keep saying, no, if you really want to do it statistically properly, you want to marginalize over all possible values of it. You want to add up. And that can be done. But it's a lot of work in the programs, because
so when you say to marginalize over it, like with DNA, you just pick each of the 4 states. So for marginalizing over a continuous trait, would you just divide it up and take 10 samples and interpolate between those? Or
no. You think of it this way: if first of all, for DNA, we have the conditional likelihood for A, for C, for G, for T. For any, I gotta get my thumb out of the way here. For any ambiguity, you would have like 1s and 0s, for 1s for all the possible states and 0s for all the impossible ones. And you just bookkeep those down the tree. You just do the same computation down the tree you would do in case of complete data, and everything's fine. For the continuous traits, these things are in Brownian motion and in Ornstein-Uhlenbeck models, which are basically the only ones that work.
I have so many questions about that, but let's finish this discussion first.
That's a different issue than most of which you have multivariate normal distribution of the tip data, of the phenotypes at the tips, the numerical values. And that's a multivariate normal distribution. It has a mean vector. It has a covariance matrix that comes from the structure of the tree. And then there are algorithms like the pruning algorithms, which which I came up with, and you can use those to more quickly do the likelihood computation, and that helps. Although you could just take that and do matrix computations and get the likelihood if you wanted to. That's slower. We'll get the same result. Now imagine that you don't, here's 4 species and they're in some tree. Imagine that for this one, we don't have an observation there.
Right.
Now the tree is only, I can't do, 3-species tree.
Mm-hmm.
And you can do the computations for the 3-species tree.
Yes.
But the matrix is different. You know, you've dropped a row and a column. Actually, since the characters are covariant, some of them will be missing and some of them won't, there's really a bigger covariance matrix.
Right.
And what you'll be doing is dropping some rows and columns from it. And that makes life harder with respect to the pruning algorithms. You could prune either the 3-case or the 3-species case or the 4-species case, but the pruning operations you do for the 4-species case don't help you with the 3. You have to do the 3 separately.
Okay.
So things just get more complicated. There's no reason that it can't be done. But it's just that who had the time to write the programs? I was busy, and nobody else has either.
Yeah. No, it's really pressing now. It's a major challenge. I guess
it's on my list of things to do.
That's
for
great.
You know, programs in my package, and I'm sure the Mr. Bayes people or whoever else are. I'm sure they're sitting there saying it's on their list of things.
Oh,
to
it
do,
is.
but
It's actually on their issue tracker. Yeah, absolutely. So, how different are terminal nodes tips and internal nodes from each other? Like we often tend to treat them as quite separate entities, but why, for example, when there's missing data at a terminal node, why can't we just think of it in the exact same way that we think about all the missing data on all of the internal nodes?
Well, I would. I mean, for DNA likelihood, we just take this vector of 4 possibilities and we, do the computation, whether you're interior node or a tip. But I think what I would do if I were doing missing data for a Brownian motion tree, I would have some symbol like NA or something. I'd have to really put a kind of, for each character, I'd have to put in a Boolean that said, is this missing? Or, is this present?
Yeah.
And bookkeep that Boolean down the tree too. And basically it says if we have 2 tips and they're sister species and the data is missing in both of them, then you want to also say it's missing in the ancestor. So, you have to do that bookkeeping.
Yeah. Okay. That makes sense. So there is so much confusion out there about missing data. And again, I think this is a consequence of a lot of the innovations in the software not being reflected in the literature, just like for tree structure. So I've, had people tell me that data is interpolated or it's borrowed from neighboring species or any combination of these things.
Not in any program that I write.
Yeah.
And I've had people come up and say, you've got a problem with missing data because if there's missing data, even say missing parts of the sequence, those species that have that stuff missing will attract each other in the tree because look, their states are similar.
Right. Like it's
and I keep saying, you're completely wrong. They are treated as missing and they are not treated as evidence for these being similar.
That's right.
And you have to persuade them and say, for example, for parsimony, no parsimony program I know treats missing data as an additional state and counts that as evidence for a relationship. They all take it into account in the correct way.
Yeah.
But the users don't understand that.
Yeah. Well, missing data, I think there's a lot of misunderstandings about how it's actually implemented how
Yeah.
the tolerance of missing data is implemented. And then that carries over into concerns about what the impacts of missing data could be. So there's very misplaced concerns like attraction due to missing data alone. But then there are some scenarios under which one can imagine missing data having an impact. For example, if there's rate heterogeneity across the sites, and then there's different structures of missing data, that could have an impact, couldn't it?
Well, it would mostly infer with what power are you able to infer the rate of evolution in a particular part of a particular molecule.
Mm-hmm. So you're not so concerned about misleading the topology or providing false confidence in the wrong tree.
Well, if you can model it correctly.
Mm-hmm.
The other thing that can happen is that when there's a lot of missing data, you're often uncertain about your alignments.
Mm-hmm.
And so a lot of people will drop those areas of the molecule.
Yeah.
Because they're not sure they have it aligned correctly.
Right.
And I'm sympathetic to doing that. I can sort of see. And I should say, by the way, in 1973, a paper by Sankoff, Morell, and Cedergren in Nature New Biology, David Sankoff and his friends urged us to integrate the topics of alignment and phylogenies, to make the phylogeny and the alignment together.
Mm-hmm.
They used a parsimony method, and that was 20 years ahead of its time,
mm-hmm.
because the field of multiple sequence alignment then went on for 20 years with people using all kinds of beautiful mathematical methods until finally, with the in the late 80s, Russell Doolittle and Des Higgins and others brought up progressive alignment methods in which you tried to infer alignments together with in a phylogenetically aware way. And finally that led to Clustow, and Clustow was so successful in getting the kind of alignments people wanted that it raised the issue. So like 20 years after David Sankoff said, these are not separable things. You do one stage and then you do the other.
Well, that seems to be the common thread, right? Like we were just having the similar conversation about inference of traits on trees, all these siloed steps.
It's the same issues. And in that case, its importance has been recognized by numerous people.
So to go back to a very disheartening comment you've made recently, so you said that BM and OU are the only models for continuous trait evolution that will work in this framework. Why is that? And why couldn't one, for example, do some sort of spectral decomposition and use mixture models or something like that to try and do more complex things?
I don't, you can make up more complex models. You can make up models that have mixtures of processes. The bookkeeping gets harder.
Mm-hmm.
And then there are issues of identifiability, and confounding.
Mm-hmm.
It's kind of built in, hard to do things other than Brownian motion and other than normal distributions. It's very disheartening because people come along all the time and say, look, the world is more complex than that. You should have a more realistic model. And I have to say to them, other models will be admitted to the event only if you can bring one that's tractable.
Yeah. Standing
there and saying it's more complicated, if you're a theoretician working in biology, you don't want to hear that. That's what people tell you all the time.
Yeah, of course.
Your models are too simple. Go away. Don't talk to us.
Now,
You know,
yeah, it strikes me that there's at least two ways that data could deviate from a Gaussian distribution. One is that the shape isn't the same, but you could still capture the variation with a single parameter. And I'm wondering, in those cases, do you think it's valid to just remap the data from whatever continuous distribution it is using quantile distribution or something into a Gaussian and then proceed on the tree as you would that way?
Well, you can do a transformation of scale and then use a Gaussian.
Yes.
That's doable.
Yeah.
And for discrete traits, for the last 15 years, I have been bugging people to think about using the old quantitative genetics threshold model, which says that there's an underlying quantitative trait. Everything is Gaussian and Brownian on that. And then there's a cutoff. So it's a threshold. You know, it's basically a scale transformation where you jump suddenly at a certain point. And then you have I've got a program that it'll be out. It's downloadable now, but it'll be put into phylip ThreshML that will do threshold.
Oh, great!
It'll do contrast comparative method-y stuff using the threshold model, actually for discrete traits, and it can do continuous traits too. And that has to be done by MCMC. It's not as simple as the others. So that's another way of doing a scale transformation. Scale transformations are possible approach.
Yeah. And the way I think about that, like a lot of times that's presented as just squishing your data to make it fit the model. But I think that the way I prefer to think about it is that one could use a different model on these data and everything would go nicely. So you could transform the model, but there are transforms to the data that are equivalent to applying an inverse transform on the model. So I see these remapping things not as squishing the data to conform to the expectations of the model, but as a way, in effect, to use a different model, but via a modification of the data rather than the model. Does that sound defendable to you, or
you could think of it either way. I think what you would do in practice inside the computer wouldn't be different.
Yeah, no, it wouldn't. So the other way you can deviate, of course, from BM or OU is to really need more parameters. So you could think of, for example, higher order polynomials. I think that's the kind of thing when people are saying, hey, it's more complicated, I need like 4 parameters in here. So why is it that we can go from 1 parameter with BM to 2 with OU? Why isn't there a larger family of models where we can add more parameters?
I think you can do things like that, but you have to be careful about a little careful about realism. I know I just disclaimed realism, but you're saying 2 parameters for Brownian motion and 1 for 2 parameters for Ornstein-Uhlenbeck and 1 for Brownian motion. I'm thinking multiple characters. With 10 characters, you have 10 parameters for the mean and 45 parameters. Let's see, 10 times 9 over 2. So that's 45 parameters for the covariances for Brownian motion. For Ornstein-Uhlenbeck, I think it's, I don't know, there's another 45 parameters or so having to do with the strength of return to the to the origin, which is not necessarily separate in each character.
Right.
There are covariant, they happen, you're in a space with 2 dimensions, you're in a 2-dimensional space, let's say, you might have some covariances reflecting the Brownian part, but the returning force could go in any direction. So you got parameters for that too. And then there's also, as you go and add more parameters, at some point you're going to have to consider identifiability, confounding.
Absolutely. Yeah.
What can you really, can you squeeze blood out of a stone? I mean, it's very easy to sit there and say, "Ooh, we have all these complicated biological processes. Let's throw in parameters for each one." But then you're going to get stuff that's not identifiable, and you won't know it.
Well, your covariance matrices will be singular in things, and people say, "Oh, my God, it's 100 by 100." But
yeah, I have. I tell people basically that we have to develop Brownian or Ornstein-Uhlenbeck models for multiple characters, and it's been done by Marguerite Butler and Aaron King in principle, but not used very much. Most people doing OU are doing it on a single character because it's hard, and there are there are a lot of parameters around, and you have to understand how they work, and most people don't.
So if one were to neglect the covariance structure, would that become a much more tractable problem then?
Yeah, but I worry about, I mean, I think that's neglecting too much. Right. Because my training is in quantitative genetics, and in quantitative genetics, people are measuring the width of my skull and the height of my skull and the length of my thumb. And no quantitative geneticist will let you get away with treating those as independent traits.
Right.
Because they know too much. They measure cows and they find out that those things are correlated.
Yeah. Yeah, absolutely. So a couple other general questions come to mind. So what are the current computational bottlenecks in model-based inference? Like what is the computer spending most of its time doing in general?
Well, I can't speak for other people's programs because they may be doing things much more efficiently than I do. So, and my programs are quite old. So I'm not sure I can give you an overview of these problems for the field right now. I think in my current versions of my programs, the likelihood computations themselves take up a lot of time.
Yeah.
And the searching of tree space takes up a lot of time. The doing of bookkeeping on the tree, like rearranging the tree, is pretty quick.
Yeah.
That's not, if you speed that up 100-fold, you won't have very much impact on the speed of the program.
Right.
But if you speed up the likelihood computations, even in a Bayesian program, the likelihood part is going to be be a big problem. And in MCMC, of course, there's the issue of how long do you burn in, and then how long do you run, and how do you assess when to stop?
Right.
The theoretical answer is very clear. You should run an infinite length of time.
Right.
People will come to me and they'll say, how do I, let's say we're doing bootstraps, how many bootstrap replicates could I use? And then they'll say, what is the theoretical best number to use? Right. And I'll say,
infinity.
And the other thing I'll say is, or I sometimes say, well, you take the cost of doing one replicate, and you divide it into your total budget.
Right, right.
And that's how many of them you do, you know.
Yeah. No, absolutely. So we actually did a little bit of profiling on phylip, and consistent with what you said, there is a function called slope curve, where the program spends 65% of its time, and you go in and you look at what it's doing, and it is calculating the likelihood. So
well, it's slope curve is getting the slope and curvature of the likelihood curves, and slope curve calls the likelihood computations. I'm not sure. The way you're profiling sounds like it's the actual slope curve computations that are slow. I'm a bit dismayed to hear that. I should work on.
Yeah.
I'm sorry.
Or there's just a lot of them. It's hitting them frequently. So
yeah. Oh, it is. You know.
And so this is for branch length optimization, right?
Basically, yeah.
Okay, so a lot of the likelihood calculations then are being spent once you've made a rearrangement, calculating these curves to try and find the optimal branch lengths on that topology.
Yeah, you can alternatively do EM algorithms. They are computationally, they're more bookkeeping. And they get slow, they converge slowly after. They're very, very good and robust in their initial stages. And then they converge more slowly after that. Yeah, there's probably, other people might have solved those problems and be running much faster in those parts of their programs. I'm not, you know, I've been working in a variety of models and a variety of tasks, and so I haven't had time to take one of my projects and really optimize it. You know, it's just it's like my tree search. My tree search algorithms are very imperfect. They're very crude, and I just had to say, well, maybe it's good enough. I got other things to do. You know?
Right. So I would be really interested if you have a bit more time, a little more time, to actually take a look at dnaml and just start in the main function and walk out to like where the key things in likelihood that we think about happen. So there's proposing the initial tree, optimizing the branch lengths, and so on and so forth. So I can go ahead and share my screen. I have
okay.
that up.
I should tell you that I'm working on version 4.0 of phylip, which won't be out until I get lots of things working and fixed and so on. So what I say about will be for the 3.69 X series.
So we'll just look at dnaml. Okay, so if we come down here, so just like any good C program here, we have a main function where everything starts out. It seems pretty straightforward. It's parsing the input files. It's configuring a few different things. And then we get down to another function that is auspiciously named maketree. And the only thing that happens after that pretty much is clean up and it prints done. So this makes me think that maketree is where all the magic happens.
Yeah, and you'll notice that it's got a loop running about how many data sets.
That's
if there are 20 data sets, that's this loop here.
Okay,
And as you say, everything get input is what presents a menu to you. It does some initialization, presents a menu to you. You choose some settings, you supply some additional information, and then it goes and calls maketree. Yeah.
Okay.
And
excellent.
and I should say that there's a Boolean called user tree.
Yes.
Which has to do if you're in user tree mode where you're going to read trees in and evaluate them. it makes a single call to make tree. If you're inferring trees, there's a possibility of the J option, which is jumble, which is changes the input order of species.
Yeah. Okay. I saw a randomize function of some sort that I think has something to do with that. So
yeah.
Okay,
Yeah, so it's gonna read, it's gonna do it multiple times, and each time it'll reorder the it'll try a different input order of species.
I see. Okay.
So let's go to make
tree. Okay, so here's make tree. Here's exactly what you were saying. Like if a user specifies a tree, and it will calculate the likelihood, and if there aren't branch links, it will optimize those, I believe.
Yeah.
But maybe let's go ahead and just scroll down to the case where a user doesn't provide a tree. So they're just providing an alignment. So here's this randomize for jumbling.
It's just going to make an array enter order, which it basically scrambles the name of it comes up, it takes the numbers 1 through SPP, 1 through species, and puts them in a random order.
Yeah. Okay.
So
that's pretty straightforward. And then I thought this was interesting to see how the tree is actually, comes into being. So my understanding of a quick look at this morning is that I think you're building a quartet, and then you're dropping additional taxa into it. Is that correct?
No, actually I'm building a trio.
Oh, okay. So that simple tree is a trio.
It's three tips. This is an unrooted tree, so there's only one possible topology.
Okay, so it's one indexed then. So that's why you enter the loop on the fourth species then.
Yeah.
Okay. And then are you just dropping the tips in so it's generating a completely random topology? They
no.
Okay.
No, not doing that. Build simple tree, let's see if I get this right, will put together a 3-species tree, and it will optimize branch lengths.
Oh, okay.
It'll call,
take a look at,
I think if you go,
yeah, here it is. Here.
Hook up, this is all just bookkeeping and it puts some initial branch lengths in 0.1. What does it do? I guess it's just using initial branch lengths of 0.1. That's it.
Okay.
So it's not doing that. Okay. I think let's go back to where we were. This is just doing bookkeeping.
Okay.
I was wrong. It does not optimizing branch lengths at that moment. And then the next species you're going to add is the fourth one. It's not species number 4. It's the fourth one in this enter order.
Right.
Enter order is 1 through the number of species, unless you're doing them in jumbled order, in which case, it's whatever that order is.
Right. Okay.
And then you're running a while loop.
Yes.
And the while loop is going to do some bookkeeping to build the new tip to set up, to make sure all the bookkeeping is done to get the characters in the character states in. And then we're going to do, what are we doing? Oh, yes. We make a copy, dnaml copy. We make a copy of the current tree, cur tree, to a tree called prior tree. We're saving a copy of it.
Yep. And
we're, of the 3-species tree, the first time through, that would just be a copy of the 3-species tree. The next time you come through the while loop, it'd be the 4-species tree and 5-species tree. And then we're going to add this fourth taxon. And that's this function addtraverse.
Okay.
And what addtraverse is going to do is it's going to take this fourth take the next species, which starts out as the fourth one being added, and try it in all branches of the tree.
Oh, wow. Okay.
It's a recursive function. It calls itself, and all it does is stick it in, somewhere in the middle of the branch, and then it optimizes branch lengths. When we optimize a branch length, we do it locally. We in effect we have peeled likelihoods down from other parts of the tree to both ends of that branch.
Right.
And then you can rather quickly optimize the length of the branch. But you then have to wander around the tree doing that until everything settles down.
Okay.
And that's optimizing the branch lengths for that one location of the next species.
Okay.
After you finish adding a new species, you then go and do local rearrangements on the tree. You do a round of you do as many local rearrangements as you can. Well, you do them until there is no rearrangement. Anyway, you know what we mean by local rearrangement. It's a nearest neighbor rearrangement. In effect, what you're doing is taking an interior branch in the tree that has two things connected at one end and two things connected at the other. And you're dissolving it and taking those four things, and there are three possible unrooted tree topologies, and you're going to try the other two. What we mean by global rearrangements is, of course, there is no such thing as global rearrangements. The ideal method of rearranging a tree will be to dissolve the entire tree and then form it again in all possible ways.
Right.
Which means looking at every possible tree topology. Of course, nobody does that. I mean, when I say it's global, is now called subtree pruning and regrafting.
Right. Okay.
Which is a sort of regarded as a moderate strength rearrangement and not a, Dave Swafford in Palpstar, he had tree bisection and reconnection, which I think he was doing the first person to do that.
Yeah.
That's a more general rearrangement. Addtraverse has an argument called contin, which you'll see. You just put a box on top of it, but no. Let me look. Okay, the third argument. It keeps moving. Boolean contin. That is, you're putting a tip into the tree, and you put it into a branch, and then you call recursively to put it in the next two branches.
Oh, so it's whether you continue or not.
Whether you continue beyond that.
I see.
In other words, it will. If you're doing local rearrangements, you can pull a species out of the tree. You pull a branch out of the tree, and then you put it in. And if you just look at the next two neighbors, the next two, and don't go beyond. If contin is false, you don't continue beyond that. And then it does a local rearrangement.
Okay.
So addtraverse is being, and this argument contin is being used to do the local rearrangements as well.
Okay. All right.
Now we would have to go back and to maketree maybe.
Yep.
Oh, yeah. And we'd have to go down to where addtraverse is. Now the first call to addtraverse says true, so it's going to take the new species that's coming in and try it throughout the tree.
Gotcha.
And for each one of those, do this branch length optimization.
I see. So to step back, so in phylip, you're spending a lot of time optimizing the topology at the moment where you're adding in each additional taxon. after you have added all of the taxa, is there further optimization, or when you add the last taxon, is the tree complete at that point?
The general strategy is to add taxa one after another, sequential addition. After each individual taxon is added, there is a round of local rearrangements until nothing improves. A general idea being that adding it in a particular place may have destabilized some delicate arrangement somewhere else, so you got to give it a chance to rearrange. When you're finished the whole thing, then we'll do a round, we'll do a round of subtree pruning and regrafting rearrangement of the whole thing.
Okay.
Until that settles down. And I'm now beginning to see what the structure is that I forgot. If we go back up, yes, it's coming to me. Can you go down a little further?
Sure. So there's this there's a succeeded true, and then we have this loop here that I was trying to understand.
All right. Things are a little out of order here. They're a little hard to follow because basically the important stuff is right near where your cursor is. Well, let's see, your cursor. No, that's my cursor. It won't help you. Right in the middle of the screen. There is this while succeeded thing.
Yes.
And basically, it's going to do rearrangements. And if your next species is not SPP, so if you're adding the species one at a time,
right?
If you have not finished, you'll do a local rearrangement. So I just put a species on the tree. I optimized branch lengths. Now I want to do local rearrangements unless it's the last species. If it's the last species put on the tree, I want to do subtree pruning and regrafting.
Got it.
And that's what this code is right in the middle of the screen is doing. It says if
global rearrange.
If you're allowing global SPR rearrangement, that's a Boolean. You can turn that off. And the next species, the one you just added, is the last one. Then do this global, then call this SPR routine. Otherwise, call the thing called rearrange. And rearrange is the nearest neighbor, local rearrangements.
Right. Okay.
And when you go up and look at it, you'll see that it calls addtraverse, but it has this contin argument set to false.
Wow. Okay. That makes so much sense.
All right. Okay. So yeah. So you can see what it's doing.
Absolutely. Yeah, that really clarifies a lot.
Not smooth it, by the way. Smooth it is some kind of thing where if you want to go faster, you can turn off optimization of a lot of the branch lengths.
Okay.
Normally, we don't turn it. In a normal run, you defaulted that to smooth it to true.
Okay. All right.
I think the things that I'm seeing down here, the if and jumble greater than 1 is all to do with if you're doing multiple addition orders, the J option. Then there's some copying of your best tree off to the best tree you found in this addition sequence is not necessarily the best tree overall.
That's right.
It should be so these dnaml copies. Well, let's see. There it says if you're on your first jumbling, copy it off to the best possible tree. But if you're later than it, first check whether the likelihood is better, and only copy it then. So that's what that's doing.
I see.
Nothing,
so it's
nothing very exciting.
Okay, so it's just keeping the best tree that it's seen so far in the jumbling.
Yeah.
Okay, that makes sense. I'll scroll down. this looks like it's still taking care of that. And then we get down to user tree, and then you're deallocating a bunch of memory.
Which, by the way, I don't really have to do. Most people wouldn't do that. And I don't think there's a good reason for me to have done it, except for some notion of obsessiveness.
Yeah, I like it. I like that a lot.
Do you need to throw away all your allocated memory before closing the program? Actually, nobody, I think any sensible programmer doesn't do that, but I did it. What the hell? I
think that makes sense. And then that's it. Okay, so this clarifies so much for me, because what I was, so to rephrase, what's happening here is there's a lot of optimization that's being done each time a taxon is added. One thing that's immediately apparent as a huge advantage of that is you're doing a lot of your searches in a smaller tree space, because you're optimizing on trees that don't have all of the taxa. And this is in contrast to what I've seen in other programs, where they'll often like build a neighbor joining tree or a parsimony tree, and then they'll take that tree and then they'll optimize, and they'll have a stopping criterion. So here, if I understand correctly, your stopping criteria is that all of the taxa have been added and you have done the last optimization. And
we've done the global, and we've tried the SPR rearrangements, and that's it. I should just say, in the future, in the next version, in the 4.0 release, we will have code to optimize, to rearrange on user trees.
Mm-hmm.
Right now, you can't do that. You can reevaluate their branches, but you can't rearrange them. The reason is just that we haven't got the bookkeeping working, but we will be able to rearrange on user trees. The advantage of that is you can then run a separate program, go off and get yourself a neighbor joining tree, bring it in as a user tree, and rearrange on it.
Right. Okay.
So that will give us, in the package as a whole, that will give us that possibility.
Yeah.
Could we go up to some of the places like slope curve and
I was just going to ask to do exactly
make new V and make new V, slope curve.
So
because I think you might want to know about those.
Yeah, that's exactly right. So our understanding, so these global rearrange and rearrange, they call a function called smooth, which calls a function called update, which calls make new V, which calls slope curve. So we can jump into that hierarchy. So you suggest at make new V?
There's also new view. New view is important.
Oh, yeah. I did see that. Actually, new view. So in our profiling, new view was about 34% of the time the program was spending was in that. And then slope curve was like 64%. So that's interesting. Yeah. Okay, so
I'll have to do something about that slope curve thing, because it shouldn't be spending that much time there. Okay, let's go look at those.
So new view you'd like to go to?
Yeah, let's do that, because we can get that out of the way, and then look at the others.
Okay, so let's see. Yeah, here we go. And so Ben Evans, who is in the local Yale Center for Research Computing, he spends a day a week in my lab, and he's the one who went in and actually did the profiling today, which was really fun. Okay, so here we are at new view.
Right. New view is the dynamic programming updating of likelihoods from neighboring nodes, or you're at a node.
Mm-hmm.
And there's a circle of little nodes at a fork.
Mm-hmm.
I think we have to be careful with our terminology, because the circle is a circle of little nodes. Yeah, there it is. Yeah.
From your book.
From inferring. And by the way, let me show you something. You showed me the front page of the book.
Yes.
Right? that's my wife's sculpture, Far Flung Tree. Here I'm moving my, there we
Oh,
go.
wow, there it is. That's amazing.
There it is. It's right in the
Oh.
corner of my office.
That is
I think,
really, really
I think the
funny.
view you get on the book is this one.
Yeah.
From about here. Just
Yeah.
wanted to.
Yeah, so if you look at the book that I wrote with Steve Haddock, there's a bird that here a sculptor from RISD made, and she actually made a series of birds. And so Steve has the original one, and then this is one of the other
Oh,
ones.
wow, there it is.
Yeah,
okay.
pretty fun.
Okay.
So,
yeah, let me just say that if you're up at a tip, there's a node corresponding to a tip, and there's a Boolean that says tip, yes, true. If you're down at a fork, the fork is a circle of nodes. If you're looking in a particular direction, the node that contains the conditional likelihood is the one farthest from those descendants. So if these are the three nodes here, and here are the two descendants, it's this thing down here that will contain the likelihood summary for all this stuff above. So that's where we are, and that's what the argument P refers to, is that node in the circle of nodes.
To that node.
So let's go down a little bit. We count the number of siblings, which will in most practical cases, the number we'll come up with is 2. There's a Boolean called initialized that says whether it really should be called updated or something, but anyway, it's called initialized, and it means, has this likelihood been calculated? Is it up to date? I think I might rename it up to date or something in the future. If it's not updated, you see right there, you can see that what it's going to do, there's a little loop going I equals 0 to numsibs.
Yes.
It's going to basically go up each of the descendants and update and call new view on the descendants.
Right.
So if this one is not up to date, go off and get updated information from each of the descendants. It's a recursive call.
Does that have to go all the way out to the tips and then work its way?
It all depends on the values of the Boolean initialized.
Okay.
If the Boolean initialized is false, it keeps going. If it's true, it stops there and backs out.
Okay.
And so this is a recursive call. Now let's go down.
So we have this loop 1.
Yeah, now the whole thing gets kind of complicated because we have categories of rates. We have rate categories, and we have some other categories that and I don't want to spend time on most of those, but that's to do with allowing variation of rates among sites, allowing a histogram of possible rates, and doing the calculation separately for each of those rate categories. And then the whole thing is also going to get involved in when we compute the likelihood of the tree. There's a Viterbi algorithm for not only rate variation at each site, but autocorrelated rate variation, which I have in this program, and most other people don't seem to think is important, and they don't use it, and they don't put it in their programs. But I've always felt it's an advantage of this program. Unfortunately, nobody agrees with me. So let's scroll down a little further.
Okay. So then we have a loop 2.
Yeah, there's some tables of e to the this and e to the that up there. It's all for the rate stuff. I'm not going to go over it.
Okay. That makes sense.
Yeah, where are we going?
So within that, so now we're coming back out, and then so we work.
Well, let's go back up a little. In here are going to be done some of the computations of transition probabilities. And all these things called sum and WWZZ and XX and VZ sum R and so on are all part of that. And I don't want to try to figure them out.
Yeah.
Yeah, these are the computations, but they're pretty hard to follow.
Yeah. Okay.
Scroll a little bit more just to make sure. Okay.
Yeah.
Yeah, those are the computations, and it's a pain in the ass, and I'm not going to explain it.
Yeah. No, that's fine.
And we come out of new view. So new view has updated likelihoods down the tree. It has done so separately in each of these rate categories at each site.
Mm-hmm.
And I should also say something else. New view is doing this separately at each site, but it's not going one through the number of sites. When we read the sites in the input file, we go over them and try to see if there are any two sites that have exactly the same nucleotides.
Mm-hmm.
Now, that's particularly important in the cases where we have closely related species, because you might have a lot of sites that are all A's or all C's or all G's or all T's.
Right.
You're going to have quite a few of those. Then there is a bookkeeping, some code that drives me crazy every time I have to look at it, because it drove me crazy when I wrote it. Mm-hmm. Which does some aliasing of those into each other. Mm-hmm. It basically makes some tables that will say, instead of going one through the number of sites and doing the calculation on each site, find the representative sites that represent those groups of aliased sites. Mm-hmm. So like if there's all the sites that are all A's,
yeah,
we'll just do the computation once for one of them.
Yeah, absolutely. Yeah.
And there's a variable called end sites, ENDSITES, which is the number of those representative sites.
And then you could just multiply
and you go one through those. You just do the computation for the representative sites, and there's some arrays called alias, ally, and location, mm-hmm. which every time I try to explain them to someone, I find I've forgotten which is which, but mm-hmm. they do all the bookkeeping for that.
Mm-hmm. Okay. So should we take a look at smooth and then step into update, or do you want to take a look at update and then work our way towards slope curve?
Smooth is just a recursive function that's calling updating the branch lengths.
Okay.
Throughout the tree, and I don't think it's worth going over. I think it's very straightforward.
Okay, so let's take a look at update then. So what is the main intent of update?
It's to get a new. It's going to call the making of a new branch length. Mm-hmm. Okay. So it starts out looking at the initialized values and seeing if it has to call new view going out into the tree to update the nearby views, the nearby, okay. I call them views, okay? That's what those first few statements are. And then it calls make new v, which is gonna update the branch length.
Okay.
And then smooth it is going to, it has a Boolean on it. Inittrav is just going to go out, and I think it's just going to set Booleans saying, set these initialized Booleans, gotcha. The ones that are looking back in towards that branch.
Gotcha.
It sets them all to false. So it just goes out recursively, sets them all to false, and comes back.
Okay.
So that's all that update has done. It's just checked the views, it's made a new branch length, and it's set some Booleans to let the tree know that any view in that direction needs to be recalculated.
Okay, and so
now we go to probably to make new v.
Exactly. Okay, so here we are. So a Newton-Raphson algorithm improvement of a branch length.
Except it's not really Newton-Raphson. it's going to do it, I think, in this case with the slope curve. So it's not going to compute curvatures, it's going to approximate them.
Mm-hmm. And that's just with the first order polynomial through the 3 points. I mean, well, second order.
It's a quadratic, you know, you have 3 points, you fit a quadratic. So you just a little formula gives you the curvature.
Yeah. Okay.
So
all right. So yeah, it's looping over, what is it looping
It's
over?
iterating 20 times.
Okay, and that's where the magic happens. It's calling slope curve. And I just want to go down. So yeah, so that's, I see. So there's that 20 times. Okay, and so should we go to slope curve then?
I think you should, because this one is being very obvious. Okay.
Yeah. So I love this comment. I was so happy when I found it. Compute log likelihood, slope and curvature at node P. So, we've stepped all the way into where it's happening.
Right. And I should say that version 4 of phylip is going to have a lot more commenting.
Oh, okay. Great.
And I think this is where you may find, I don't know, we may find the guts here. You know?
Yeah, they are in here. Yep. Okay, so initializing some things. What is, so back is the ancestor? Or?
No, in that tree structure where each node, you know, the back means outwards, going outwards towards the neighbors.
Gotcha.
It's probably not, it's not very well named. I should have called it out or something.
Okay. Okay, and that, well, you could talk me through it and I'll scroll down as you like.
Yeah, I'm not going to give you a complete explanation, but I start out with pre-tabulating some exponentials. Then I go, now here's the loop goes up to end site. End site are these representative sites.
Yes. Okay.
There it is. The sites have different categories, and there are user-defined categories as well as the multiple rates that you need for the approximate gamma rate variation. Again, I'm not going to go through that.
No. So I guess
so you're going down. I think here we're really getting into the guts. Basically, this is the guts of the transition probability stuff.
Yeah, I was surprised to see these exponential calls up here, but not actual matrix exponentiation. I guess you're implicitly doing the matrix exponentiation.
I don't know what matrix you're referring to.
Well, like if you had your Q matrix of
oh no, we're using a particularly limited set of models. You know, we're using F84. I could make this do HKY. I just never got around to it, but I need to do that. Because of those special models, I don't need the Q matrix.
Great. Okay, that makes sense.
Yeah.
Okay, and yeah, so then we're down and actually calculating
some pieces that are needed to do the transition probabilities.
Yeah, exactly.
Maybe we are computing the curvature exactly here.
Yeah, exactly.
I think we're doing we are not doing this stepping of 3 different values. We're just taking one point and we're computing the actual curvature and the actual slope.
Oh, so you analytically come up with the curvature.
They're analytical. In this program, they're analytical. In dnaml, which is the ultrametric version of the program, we have to do the other.
Gotcha. Okay.
And
then that's it. Okay.
Right down at the end of slope curve, let's see, we get the slope and the curvature, and somewhere in make newbie, we're going to use them.
Okay.
And let me just see, let me just see, like slope curve. I think I'm embarrassed to say it's bad programming practice. Those are globals.
Yeah,
So
they're not returned.
they're not returned. They're just globals. In the version 4.0, we're doing a lot less globals and a lot more returning.
Okay. Yeah.
So now we go to make new V's. Next thing down.
Yep. And then that brings us back. So we stepped all the way in then. So that gives a really great overview of the overall approach, the overall structure. And
Yeah,
then
I
all the way
realize we're
down.
running out of time. Let me just take a peek at make new V again. Make new V
Absolutely.
again. Yeah, it's doing the slope curve. And then we go down a little more. There's some stuff about saving newer, if the first time you set aside some likelihood values and you're making sure that you got better ones, basically. Go down. Yeah, and here we go. Newton-Raphson forced up hillwards, right up at the top there. Slope over absolute value of curvature.
Okay.
And that's to keep you from Newton-Raphsoning downhill, either past the optimum and further downhill,
Right.
or sometimes if the curvature is the wrong direction, like if your curvature is positive, Newton-Raphson will go downhill. So that's what that absolute value is supposed to do. It forces you at least in the right direction, maybe not by the right amount, but at least in the right direction.
And then what is this retract 95% of way back?
It basically is going to set the iteration count suddenly up to 20, so the thing will stop.
Okay.
And for some reason, I'm doing a weighted average of the new and the old, mostly weighted towards the old. I don't remember why. There's some reason why that numerically is maybe a little better. I don't know.
Yeah.
And you'll see down at the bottom of make new V, I'm setting V to Y old, the last value that had better likelihood, and out you go.
Okay.
And I set the current likelihood of the tree, the likelihood attribute of Kerr tree to the likelihood.
Yeah.
The log likelihood.
That was so interesting. It really clarified a lot of things for me at all levels, from the biggest picture down to the nitty gritty. And that's exactly what I was hoping for. So it's pretty interesting to like look at this and think about a few different ways like one could go for thinking about how to speed up likelihood, which would be one problem to work on.
Yeah.
How much? So this again gets back to there's two sort of orthogonal ways to speed up likelihood. One is to reduce the number of things you're computing, either by getting as quickly as possible to the best tree. So working on proposal mechanisms and things like that. So you don't spend a lot of time on suboptimal stuff. And the other one is to actually speed up the math. What's your take on using like hardware acceleration, GPUs or FPGAs or anything like that? Is there room for that? You hear murmurs of this every few years, it seems like.
Well, yeah, and there's whole projects have been done to make code that everyone could use in C++ to do hardware acceleration. I think it's all worth doing. I never had time. There's things that could be done in profiling. There are things that could be done on more elaborate tree search, although that'll slow things down. RAXML, which Alexis Stamatakis and his group have done a huge amount of bookkeeping programming, because this aliasing thing I described to you, where you look at things that have exactly the same pattern. They've described it in their papers. They go up into branches of the tree and take just the set of species that are up there, and they do aliasing on those. So every time they rearrange a tree, they have to reconsider some of that. And the amount of
it's extraordinary
bookkeeping is I hope they're all still in good mental health after doing that, you know. And they found that that this speeded things up a lot.
Yeah. Yeah, and he was also trying graphics cards, and one of the limitations, this was maybe 8 years ago when I was talking to him about it, and he noted that the graphics cards at that time, most of them had single precision, so 32 bits for the floats, which just wasn't sufficient. That leads to a lot of.
phylip was developed to make multiple methods available to people, initially mostly parsimony methods, but some distance methods.
Yeah.
And let them choose among the methods. It did not work. People first decided what method they want, and then they say, do you have it in phylip? And if they did, then they went and used it. It wasn't intended to be the fastest program in the world. The hope was it would be good enough. And it wasn't intended to perfectly find the absolute best tree all the time, because we're going to be doing bootstrapping. And with bootstrapping, there's a lot of noise just comes from the bootstrapping. And you don't actually, like Ferris has written a paper somewhere saying the same thing. You don't have to find the absolute best tree, because you're just going to be looking at the distribution of trees. And more recently, phylip is, I think a lot of our traffic, a lot of the uses of it are in teaching. And people have told me that they like it because the documentation is good. I claim it to be the best documentation in the field, but we'll see. But the other is, they can, if you're doing bootstrapping, you can see you have to do several steps yourself. You have to do the sampling by running seqboot. Then you have to feed that into dnaml, or if you're using distance matrices, seqboot, then a distance calculation, then the tree. And they find that very useful for their students' understanding.
Absolutely.
But it's basic transportation. It's a Volkswagen Beetle. It's not a racing car. And
and that just helps it be more understandable. That's another reason that I want to step through it with you first before looking at a lot of the other phylogenetic programs with other people, is for exactly that reason. And I just really appreciate having a tool in that space.
I hope that we'll have 10 years from now, if I'm around, I'll be 88 years old then. We could have a phylip 50 symposium.
Oh, that would be so fun. That would be fantastic.
And I hope I'm still distributing it.
Let's do it. Count me in. Hopefully this pandemic will be over by then too, so we can all actually do it in person.
I get my first shot, my first inoculation Monday.
Wonderful. Oh, that's great to hear. That's really exciting. So, as far as like a final parting thought, like what surprises you about the problems that aren't receiving the attention that you think they should now? Is there anything that if you were starting as, a graduate student right now, you would want to tackle, or that you would suggest to someone else to tackle?
I've always complained that there's not enough work on robust method, not so much, robust methods, kind of non-parametric approaches. Although my whole emphasis has been on doing parametric stuff. And although people have claimed that for parsimony, I'm less sure it's true. The problem is that with phylogenies, the tips are not independent. They're not independent, identically distributed. In fact, that's the whole point of phylogenies, is that the tips aren't independent, and it'll tell us something about how. So that has sort of deterred conventional statisticians from coming in and saying, here's some permutation methods you could use. Here's some. I think there's a lot to be done in the Brownian motion, Ornstein-Uhlenbeck with multiple characters area. I am working with Fred Bookstein, who is Mr. Morphometrics, and I are working on how do you do morphometrics on phylogenies? And we're finally, it's taken us 10 years, but we're finally making some progress there.
Yeah. And I think a lot of that applies very directly, as we've discussed before, to functional genomics traits, to think about how to analyze gene expression data and other genomic attributes at scale.
Yeah, one issue is going to be with gene expression data is it's a quantitative character, but is it a polygenic character? Our models are polygenic, you know, which is fine for, you know, the length of my finger. You know, there's many genes will contribute.
Yeah.
But if I have the expression level of the malate dehydrogenase gene, is that controlled by multiple sites in the genome, or is it controlled by just a few neighboring sites around?
So I think
that
that's
gene,
exactly
you know,
it. So I think it is polygenic, but we can't assume it's many. We're going to get down into these integer rangers of effects where you can't assume, you know, central limit theorem type distributions. So exactly. And I'm wondering what that means. Do we address each of those factors as an independent component of a mixture model, which is exactly why I was asking you about non-OU, non-BM models.
I don't know. I haven't thought further about that. So I think I should not venture too many opinions, but that's where I'm concerned. I'm concerned in models like that as well. As you know, you have concerned yourself with it. There is the issue of identifiability and confounding and dimensionality, which people don't understand very well. They seem to think that with 50 species they can and 10 characters they can estimate thousands of variables. I'm not so sure, you know. And so, you know, there is all that.
Yeah. Interesting times. Yeah, for sure.
Yes.
So thank you.
I was very pleased to see that when they got coronavirus, when they started working on coronavirus, the people here in Seattle, Trevor Bedford at the Fred Hutchinson Cancer
amazing
Center,
work.
He's a very good guy, and he's working. He's using likelihood and Bayesian methods. You know, Eric Matson at the Fred Hutch doing stuff like that too. I was very pleased to see trees showing up immediately and with little numbers on their branches.
Wasn't that fantastic? So, you could just watch the tree grow in real time. It was incredible. So, and really shows the real time value and power of phylogenetics. Absolutely. So
I better let you go get dinner.
Oh, well, thank you so much. This has been a real pleasure, and I really appreciate it. So
that certainly we got more done than I thought we would.
Yeah, we sure did.
All right.
Okay, thanks
good
so
to
much.
see you, Casey.
Likewise. Take care.
Good night.
Great to see you, Joe. Thanks a lot. Bye.